All right, I want to set something up for you real quick. So let's take a look at I think this is question number. What question is that, Dalton? In that homework?
This one?
Yeah.
18.
Okay. 20. All right. So question 20, guys. Out of 11.2 is a question that I've been having all day long, which is not out of the norm for this assignment. But I want to kind of talk about what you're actually being asked to do here. Okay. So if I take a point here, let's see here, 2, 0, 0. Okay, so let's go 2, 0, 0, 0. Let's go 0, 0, 0. Let's go 2, 0, 3. And let's go 0, 0, 3. So that's kind of how we plot points in three-dimensional space. We have a z coordinate, essentially. But you're being asked in that homework assignment to look at this polygon and see if you can rotate that polygon and develop a three-dimensional picture. Okay, they call it a solid of revolution. Okay, and that's actually a calculus concept. And this question is really a calculus question, but we have enough geometry to be able to answer it. Okay, what they're wanting us to do is to take that shape, and they say to revolve it around a particular axis. So you need to make sure that you pay attention to the right axis, because working with Dalton, he had the right thing, he had the right number for around the y-axis, but his question was for the x-axis. So make sure you understand that there is a difference. If I revolve this around, let's say, the y-axis, okay, and I'm going to use K as my angle of revolution, and you can start to see that this would be a shape that's kind of what we're doing here. We're taking this shape and rotating it. But what I can do is I can trace this. And basically what it's going to do is just kind of highlight the places that rectangle has been as I rotate that shape around the y-axis. It's kind of the idea is if you were to look at the fan up there and you were to look at it stopped, your eyes see 3 separate blades, right? But when I turn that fan on, because that fan is going faster than 24 frames per second, your eyes and your brain interpret that as a circle, right? Okay? Same idea we want to kind of think about here. We're spinning that rectangle around that axis very fast. Okay? And the only thing that I could see then visually would be that cylinder. That's called a solid revolution. Now, based off of that rectangle, okay, look at that rectangle, can you determine what the radius would be of that cylinder? It'd be DC, which is the width of that rectangle, right? Does that make sense to everybody? So this distance right here is the radius of that cylinder. This distance here is going to be the height. That's the altitude. So now that you have those two values, R and H, you plug them into your formula for surface area. We'll see a similar question later on about volumes. Okay, so that being said, that's awesome, but let's go back. Okay, and now I revolved around the blue axis. Let's revolve this thing around the red axis. And if we do that, what is that shape? Cylinder. Is it the same cylinder? No. What is the radius now? It's now this distance, right? And that was the altitude of the last cylinder, right? So here, based on the axis they tell me to rotate around, I get a different R and I get a different H. And that matters because in my formula, R and H are having different operations done to them. Okay? So order of operations tells me essentially that cylinder is a different surface area than that first one. Does that make sense? Okay? So what are we going to do later? Later, we're going to do this. We're going to take that. We're going to take C and we're going to get that out of there. Oh, Guess I'm not going to do it that way. Let's just delete C. And now I'm going to look at that polygon, and I want to ask, if I rotate that polygon around that axis by K, what is that shape going to be? It's going to be a cone. Okay, I don't know why I didn't trace. But we're going to get that cone. And now what is the radius of that cone? It'd be that distance right there of that triangle, right? What's the altitude of that cone? D to B, right? Okay. Now, here's the question. If you rotate around that axis and you get that cone, what does it look like if you rotate around the other axis? Is it a different H and a different R on the other axis? If I rotate around that red one, isn't R going to be that distance now? And H is going to be that one, right? And that then affects the surface area. Okay. Okay, so what if we did something like this? Take that shape. Rotate that shape around this axis. We get that, right? Looks like a, okay, looks like a Reese's cup is what people have been saying all day. Cupcake, I've heard. Bottom of a cupcake. Okay, trapezoid meets cylinder. Okay. Is it a cone with the top chopped off?
Yeah.
Okay.
Volcano.
Okay, so Canyon, when you left the circus, did you see elephants standing on things like that? You guys ever seen that?
Yeah.
You've seen seals on those things, right? Okay. It's kind of those platforms, looks like a volcano. Does anybody know the math word for that? I'll give you a for the year if you can tell me the math word for that shape.
Wait, for the year?
The year. I'll go back and change all your. Give you 5 seconds. Somebody knows it?
Hydrical cylinder.
That's a frustum. Okay, so that shape is called a frustum. Okay, so can we do something like this? Can I take?
Hey, did you just in the other class?
Huh?
Did you just in the other class? Like,
Yeah.
Like, hey, what's his name?
Yep.
I know, right? Yeah.
No, they're gonna be like, oh, they told you.
All right, what if I take that shape and rotate around a different axis? Am I going to get the same thing? Am I?
No.
Okay, it looks like a circus tent, right? Okay. Now, why does it look like a circus tent? Was it a rectangle and a triangle stuck together? All right, so what we do in a calculus class, guys, we know the equations of the lines that make up that trapezoid. Okay? We know the equations of the lines that make up that trapezoid. The line segment DC is y equals 3. Okay? BA is y equals 0. D to B is x equals 0. And CA, we can find that by taking those ordered pairs and creating an equation for that line. Be pretty easy. Once we have that information, through calculus concepts, we can find those volumes almost instantaneously. Okay? But finding those volumes, it's going to incorporate a little bit of our geometry concepts here to be able to do that. Does that make sense? Okay? A lot of the things that you guys deal with on a regular basis, let's say that we look at, let me zoom in here real quick. Let's go back. So let's say I take D and move it to 103. Nope. 013. There you go. Let's rotate this one. If I rotate that one, okay, start to see what this thing would look like. What's that give me? Okay, a washer. Somebody said washer. Somebody said hose. A pipe. Roll of toilet paper. Okay. So there are things in our everyday life that we can learn the volume for or the surface area for. Now, the reason I want to maybe know the volume of a pipe would be pretty obvious. Okay, I want to know the amount of kind of fluid that could run through that pipe at a certain time. But we can use that rectangle, dimensions of that rectangle, to help us figure that out. If you go to Lowe's, Menards, Home Depot, wherever, go to the plumbing section, go to the gardening section, get a garden hose. Every time you look at the label, it's going to say I.D, O.D, or I.R, or O.R. And that stands for inner radius or outer radius, or inner diameter, outer diameter. And that information is this right here. The inner radius, so if I look at this shape right here, the inner radius would be from the blue line to D. Does that make sense? It'd be the radius of that inner cylinder. The outer radius would be from that blue line to C. Does that make sense, everybody? Okay. And now why we would want to know that at Lowe's or Menards, wherever, if I'm getting like pipe to transfer water in my house or wastewater or something like that, I want to make sure that those pipes fit snugly together so that when I do end up gluing them or soldering them or whatever, there's no leaking. Does that make sense? Okay, you obviously don't want water leaking in your home. But if you get the wrong ID, OD, inner diameter, outer diameter for those pipes, they're not going to fit snugly together. Okay, so a lot of the information that we talk about here in this course, you can start to translate over into seeing being used in real life applications. No. No. You have to have metal. You can. There's glue that you use on PVC that actually kind of melts the PVC and then sticks it together. Yes. Yep. But you can't. No, you can't solder it. Soldering is like metal. Okay, so hopefully that helps with that question and questions like that. Okay. The reason I want to talk about that, we took maybe 10 minutes talking about that, is there is a question on some of the practice EOC tests that I think it's in practice test 1 here. I got. Excuse me? I think there's a chemical reaction that happens there. I think there is.
I don't burn it very good.
Well, I mean, just enough to make it bond. All right, so this question here, this is a sample question, which means that it was a previous question on a previous test that was actually given to high school students. And it says, triangle ABC is shown, which three-dimensional figure results from rotating the triangle 360 degrees about line segment AC. Visualize taking AC in that triangle and rotating it 360 degrees. What's going to trace out? Going to trace out a cone. Okay? So that question in our homework in Math Excel is targeting this idea for the end of course exam. Hopefully it's a little bit easier on the end of course exam than what it is in our homework. And I really hope that that's the case, is that our homework is harder than the end of course exam. Okay?
This is a hard homework.
Because then when you get to the end of course exam, I've been here, I've done this was easy. Okay? All right, so 11.4. Let's get into that. 11.4, talking about volumes of prisms and cylinders. Tomorrow we'll talk about volumes of pyramids and cones. And then Friday, kind of wrap up any loose ends with this chapter. And then next week get into circles. I did make kind of a oversight with the calendar for the remaining couple weeks, not realizing that next week you are taking some end of course exams next week, right? Your English ones are next week. I believe English and science maybe. So there's some. I could be wrong on which ones they are. I'm focused on the math one. That's May 1st. But you've got some next week. So we got some 2-hour delay, 3-hour delay possibilities next week. I'm not sure which. I got to look at what the.
If you ain't got to test, you ain't got to come in.
Huh?
If you don't have to test, you ain't got to come.
No, I don't think. So, that being said, depending on what those are, 2 hours or 3 hours. If it's 3 hours, we'll have 20-minute classes. If it's 2 hours, we'll have half-hour minute classes, right? So, doing the circle stuff next week, we're going to miss out on basically 40 minutes overall in regards to doing that. Okay, basically miss a day because of those delays. Does that make sense? So that kind of shortens our time frame a little bit, not much, but a little bit. So volumes of prisms and cylinders. This is by far the easiest formula that we're going to see in this chapter, maybe in this course. Volume of a prism is capital B times H. Now, it might make sense to talk about what volume is first. Volume is the space that an object occupies. Okay, the space that an object occupies. My thought is that a lot of you are probably going to connect volume with liquid. Okay, which is fine because that's probably what you deal with volume in regards to science class the most, right? But every shape, every solid, every state of matter has a volume. Okay. All right. Okay. In volume, in science, maybe you know that volume impacts density, right? Yeah. Okay. Some questions on there dealing with volume, right? Okay, so for prisms, capital B times H. H, so we're finding volume, we're finding volume of a prism. So that H that you see in the formula is H of the prism. What's capital B probably stand for? Area of the base. Okay? Now, when you do the area of the base, there might be a lowercase h that shows up in that, but it's the H, or the altitude of the base. Okay? That H up there that you're seeing in the formula is H of the prism. All right? Is that cool? Very simple formula, B times H. All right, so the rectangular prism. Rectangular prism. You guys probably know, working in 7th grade, 8th grade, 9th grade, length times width times height, right? You want to use it, that's fine. Okay? Length times width times height. I don't like to use that because it's another formula I got to remember instead of just capital B times H. But if I go volume equals L times W times H, L and W, those are the dimensions of a rectangle, right? Those are the B and the H of a rectangle that we talked about in chapter 10. So that is still a capital B. That thing I got curly braces around, that is the capital B. So it's really not learning a new formula. Does that make sense? Just a way of kind of restructuring our formula. All right, so with this shape up there, okay, let's talk about finding the volume of that rectangular prism. Like all rectangular prisms, doesn't matter what my base is. No. Okay, so what do you want your base to be? 10 and 20? Okay, so you're saying that that is going to be your base. That's fine. Okay, so if I take that as my base, so that's capital B, right? So I'm going to, it's a rectangle, so capital B would be 10 times 20, be B times H, right? So that's 200. Okay, now if that's my base, what is H going to be? Yeah, H is the distance that connects your two bases. So multiply that by 24. Okay, if I multiply that out, 200 times 24, what's 2 times 24? 48, right? And then you got 100 there that we still need in there. So we get that. Okay. Now, if I do volume is equal, a lot of people throughout the day have said the 24 by 20 is the base. What's 24 times 20? 40. And then H would be 10. Does that still give me 4,800? Okay. Now, what was the unit here on that one? Centimeters. What was the unit on that one? Centimeters. What was the unit on that one? Centimeters. What's centimeters times centimeters times centimeters? Centimeters cubed. Now, let's make some comparisons, some common, hopefully common knowledge remarks here about cubic centimeters. Okay? Okay, so a cubic centimeter, 1 cubic centimeter, kind of visualize this. You guys go to the store and get cubes of cheese, right?
No.
You know what a cube of cheese is, right?
No. Yeah, the
little tiny cubes? Yeah. Okay. So those are, Like if you had one of those that was 1 centimeter by 1 centimeter by 1 centimeter, every dimension on there, every side edge was a 1 centimeter, you have 1 cubic centimeter of cheese. Okay? So I like doing that because it gives me a visual of how big a cubic centimeter is. Does that make sense? Okay. Now, a cubic centimeter has another labeling that we can use. 1 cubic centimeter is the same thing as what we say is 1 cc. Ever been in the medical field and somebody says, hey, I need 50 cc's of morphine? Well, that means they need 50 cubic centimeters of morphine. Does that make sense? Okay. Now there's another, think about this, people that are like interested in dirt bikes and trucks and all. So now like cars are going to be labeled in their engines are going to be in liters. Okay, like 2.4 liters or 5.4 liters, something like that, right? And that's what? What does that refer to?
Liters.
But isn't that the amount of gas that can fill your cylinders at one time? Okay, because then that converts over, the combustion converts over to energy and all that kind of stuff, right? So the bigger that liter is, the more, it's basically the volume of the cylinders inside your engine. Okay, the total volume of it. So those are all things that maybe buying a car you would want to know. Okay, if you buy a dirt bike, maybe you want to know it's 700 cc's or maybe it's 800 cc's or something like that, right? Okay, so those are things. Maybe weed eaters. Weed eaters have cc's written on them. Okay, or leaf blowers. Okay. Yeah. So the cc is telling you about how much volume is in the cylinder and how much gas can be put in that cylinder at one time. There's another unit that we use for cc. Does anybody know what 1 cubic centimeter is equal to in liquid form?
1
Milliliter.
Say again?
Milliliter.
Awesome.
Radical.
Okay? So it'd be 4,800 milliliters if we're talking about a liquid conversion now. So milliliters, okay, that is when we're talking about, I guess maybe you could talk about it in regards to gases as well. But if I've got something that is, let's say I want to find the volume of like a concrete block, I'm probably not going to use milliliters, right? I'd probably use cubic centimeters. Okay, but if I'm trying to find the volume of a, a juice box, okay, and it's got juice in it, maybe I would use milliliters. Does that make sense? Okay, but those are all different ways of talking about the same 1 centimeter by 1 centimeter by 1 centimeter unit. Okay. All right, let's do this question. Let's find the volume of that. I'll give you guys a minute. You guys come up with what the capital B is in this one. Give you about 3 minutes to do that. When we started talking about prisms, we said the number one thing you have to first find is the base, and the base is going to be the two congruent parallel polygons, right? Okay. Therefore, the only two polygons up there that are congruent and parallel are the triangles. Now, I also told you a quick way of doing that and figuring that out is to choose the surfaces that are non-rectangular, right? And that will 99.99999% of the time get you the right bases. And if it's a rectangular prism, then it doesn't matter.
For this exact, for finding volume, would that really matter, though, because you're still multiplying the same three numbers?
No, you're not. Because here it's not length, width, and height.
Yeah, but I know that
Right, so volume is B times H, right? So here, B is 1/2 BH. So that's why it matters here, is because lowercase b and lowercase h are getting multiplied by half. So we got to make sure we get the right numbers being multiplied by half. Now, if it was a rectangular prism like the last question, then no, it doesn't matter which one you each go length, width, and height, and multiply them in any order you want to. Okay, so now here, if our base is the triangle, what kind of triangle do we have? Equilateral. Good. So it's 8, 8, and 8. If it's equilateral, it's also equiangular. And if I want to find the altitude, doesn't the altitude go from there to there? That's H, right? What does that do to an isosceles triangle's vertex angles? Splits it in half, bisects it, okay? So this here, this is 30, right? What is this? 4. So now if that's 60, what is this? 4 radical 3. So now, you got 1/2. What is B for that triangle? 8. And H is 4 radical 3. 32 times 1/2? 16. So 16 radical 3 is the area of that triangle. We've done that multiple times, guys. That should be throughout your notes at least 3 times somewhere. Okay? Now, we've also talked, now we only did this once, but we also talked that there's another formula for that. There's a special formula for an equilateral triangle. And it is found using this exact same philosophy, this process, but instead of using 8 here and here, we use S. And this becomes S over 2. And this becomes S over 2 radical 3. And then we plug it into this, we end up with the area of an equilateral triangle to be S squared radical 3 over 4. So we talked about that. So if I use that formula, what is S in this case? 8 square that, you get 64 radical 3 over 4. What's 64 divided by 4? 16. So I get the same result, right? Is that quicker? Okay, so the payoff, though, is that, yes, it's quicker, but now in my mind, I got to remember one more formula, right? Okay? Where, or unless I write down, yeah, but then I got to know that I've got it written down somewhere, right? And I got to keep that with me all the time. So in regards to learning more formulas, there is payoffs and efficiency, but the cost of that is maybe memory of additional formulas. Okay? So 16 radical 3, that is capital B right here, right? Yeah. What is H of my prism? 10. Okay. So 16 radical 3 times 10 turns into 160 radical 3. Now what is my unit? Inches cubed. Okay? Now, if I had 160 radical 3 inches cubed, or cubic inches, and I ask you how many cubic feet is that?
That is...
What do?
160 by 12.
Okay, I do not disagree that I divide by 12, but that's not all I do. Because thinking about this, if you divide by 12, what you're doing is dividing by 12 inches, right? And if I multiply by 1 over 12, that's the same thing as dividing by 12, right? So what two things have 1 and 12? If this is 12 inches, this should be 1 foot, right? Okay? Now when I do that, what did I really multiply by? I didn't multiply by 1/12. Look at the unit. If you had in front of you, you multiply by 1. If you had in front of you, you had a foot. You had 1 foot. Let's take a ruler. And no markings on it. Okay? And then you took another ruler and it had 12 markings on it. If you put those two rulers on top of each other, are they the same thing? Yes. So 1 foot divided by 12 inches, it's the same object divided by the same object. And that is always 1, right? So I'm not altering, I'm not adjusting this volume when I convert it. And that's important to understand. When we change to a different unit, you're still having volume. If I have a gallon of milk in my refrigerator, and then I explain how that gallon is now X amount of liters, is it still the same amount of milk? Yeah. Okay? If I walk 12 feet, that's the same thing as walking 144 inches, right? Okay? Same thing happens in volume. Okay? We have conversions. Now, the only thing in regards to volume, if I do this, if I just do this, all that has happened is I converted that 8 inches into feet. Does that make sense? I've turned that into 2/3 feet. But don't I need to turn this one into 2/3 feet? Don't I need to turn that one into 2/3 feet? Don't I need to eventually turn this one? I guess, actually, it'd be kind of those three. Those three are the ones that, and it's actually the 4 radical 3 and the 8 that I'm converting. Does that make sense? Okay. But I'm converting the 3 dimensions that I used to come up with volume. They were all in inches. Now I need to convert each one of those into feet. So I need to do this not just one time, but 3 times. Okay, so what's inches cubed mean? Inches times inches times inches. So right now, those cancel, don't they? One's in the top, one's in the bottom. So now I'm going to multiply by 1 foot over 12 inches again, and now that one and that one cancel, right? And then I multiply by 1 foot over 12 inches, and this one and that one cancel. And now if I multiply straight across, what are my units left over? Feet. Units, feet times feet times feet, feet cubed, right? No other units left over, right? Multiply straight across the top with my numbers. 160 radical 3. Multiply straight across the bottom. 12 cubed, which I think is 1728. Okay? So people say divide by 12. Well, I only divide by 12 if it's linear. Here, it's 3-dimensional. Does that make sense? So I divide by 12 3 separate times, which means I divide by 12 cubed, which is 1728. Okay? If it was an area, I'd divide by 12 squared, right? So we got to talk about what our units are. Are they squared? Are they the third? Or are they the first? Okay? Somebody in the last class said, well, why do I have to do it that way? Why do I have to write all 3 of those out? Can I do this? Can I go 160 radical 3 inches cubed times, now they know, well, I need inches cubed down here, and I need feet cubed left over here, right? Does that make sense? And they say, well, those are going to cancel. And now here's my argument. Did anybody know that in 1 cubic foot, when I have 1 foot by 1 foot by 1 foot block in front of me, that is 1728 cubic inches? No, you probably didn't know that. Okay? Now, maybe you do now. Okay? But they said, well, I'm not going to do that. I'm going to say, well, if I've got 1 foot by 1 foot cubed, or 1 cubic foot, that's 1 foot by 1 foot by 1 foot. That's 1 cube. And then 12 cubic inches would be 12 inches by 12 inches by 12 inches. That's 12 cubed. Does that work? Absolutely. So you can do it that way if you want to. But I think doing it that way, writing it in a more concise way initially, loses an understanding of what we're really doing. If you can understand that one up top, where we've got that box around things, you can set that up, you're going to convert every single time correctly. Okay? And then if you start understanding that pretty well, you can then make that jump to writing them a little bit more concise down there at the bottom. Okay? Hopefully you've done some of that stuff, like in science class, you've worked with changing things from grams to moles, moles to grams, and trying to talk about how, if I start with moles, what do I need to multiply by so I can get grams? Then I got to have moles on the denominator somewhere, right? Or vice versa. If I start with grams, I want to turn into moles, then grams need to be on the denominator somewhere, and moles need to be in the numerator. Okay, on my conversions. Okay, using whose number?
My number.
Avogadro's. Okay, so those are. He's that guy that makes those little green fruits, vegetables, guacamole. Okay. Yeah. Yeah. Something nasty. All right, so here we've got the volume of a cylinder. This is not hard because a cylinder evolved from a prism, right?
Right.
And we talked about at one stage it's a prism, the next stage it's a cylinder, so the volume cannot change that much. So the volume formula for a cylinder, capital B times H. Volume for a cylinder, capital B times H. But what is B always going to be for a cylinder? Area of circle. So then they give you this more specific formula, pi r squared H. And that's the thing, guys. When you do these 3-dimensional shapes, and there's always a circle involved, so a cylinder or a cone, surface area or volume with those, they're always going to give you the specific formulas, pi r squared H, or 2 pi r H plus pi r squared, 2 pi r squared, things like that, pi r L. And it's just because that base is always a circle. Okay? But now, just like we did in surface area, we have to go through and be able to find R and H for a particular cylinder. There might be different various ways of them doing this. We might go back to that question we did at the beginning of the class and say, okay, now what's the volume of that revolution, or that solid of revolution? Okay? Well, now you know how to pick off R and pick off H for that picture. You should be able to plug into this formula. Okay? So in this situation here, let's find the volume of that cylinder. We've got pi. What's R squared going to be? 9. Now what is H going to be? 8. So what do I get? Okay, so now what if this was a can of pop? Would I use cubic centimeters maybe? What would I probably use? Milliliters. I'd probably call it 72.5 milliliters. Okay. But there's nothing wrong with saying cubic centimeters cubed like that. Nothing wrong with saying cc. Okay. But maybe milliliters is more appropriate for that context of the problem. Okay, so you're going to see things like this. I'll give you a couple more questions here that we'll kind of work through quickly. Want to know the volume of this aquarium. Okay. And there might be several reasons for wanting to know the volume of this aquarium. Maybe this is like a big aquarium. Maybe these are like feet instead of inches. It's a big aquarium at like SeaWorld or something like that. And we want to pump it out. Okay, and if you've ever seen the pumps at those facilities, they take up giant buildings. Okay, and we're pumping this water out, and we would want to know, when can I start pumping it out, and can I go home, and then come back later? Okay, well if I go home, and it drains itself, and that pump keeps running for 2, 3, 4 hours with no water running through it, what's that pump going to do? It's going to seize, right? Because the water going through it cools the pump, right? So if there's no water going through it, that thing's going to burn up. It's going to get really, really, really hot, create a lot of friction, and it's going to seize. It's going to basically melt the metal together, right? So that's a problem. But if we know that there's a rating on every pump that says like gallons per hour, gallons per minute, or whatever, if I know how much gallons of water I have and how fast this pump can pump it out, I can do a little bit of math, and I can now know, hey, I can take a 45-minute hiatus, disappear, and then come back and nothing be wrong. Does that make sense? Okay. So that might be one reason why. Maybe I want to know the volume of that fish. Okay. Yeah, there's a fish in there, man. I want to know the volume of it. Okay, so I could take that fish out and measure the height of the water in the aquarium, right? Okay. Then put the fish back in and see now what the height of the water is, right? So finding the volume of the aquarium filled with water without the fish, and then find the volume of the water with the fish. Now I can find, and subtract the two, that would find me the volume of the fish, right? So they might want to know that for, like, those big aquariums at SeaWorld might have whales in them. They might have, and we can't put a whale on a scale very easily, can we? But can't we kind of maybe figure some things out that would allow me to find? Okay. All right, so let's just go. This is a composite figure. That's what I'm trying to get at here. Composite figure. So we need to chop that part off, right? And now it breaks it down to a prism and a half cylinder. So can we find the volume of that prism pretty easy? Okay, so it'd be 24 times 24 times 36, right? We figure that number out, be good to go. Now I'll find the volume of this cylinder. So it'd be pi r squared H, right? But then you're going to divide that by 2 to find the specific half cylinder's area, or volume, right? So what is R?
R is 12.
So you get 144, and H is 24. And then I would divide by 2, right? Will that 2 go into this 24? Okay, so now I can take 24 squared times 36, get that volume. Take pi times 144 times 12, get that number. What would I do with them two numbers then to figure out the volume? Add them together. Okay? There are a lot of things, guys, in the real world that we encounter on a regular basis that we want to know the volume for, but they're not really nice, easy-looking traditional prisms or traditional cylinders. They're a combination of those things, right? Okay. Most situations that we come across when we're trying to find a real volume of something is that you have to realize that you've got several shapes. Like this water bottle back here. I want to find the volume of this water bottle. Okay. It's roughly a cylinder. Okay. Roughly a cylinder. But at the top, there's kind of a conical part to it, right? Okay. And then if I go back to the cap, there's another cylinder here, okay? So the composite aspect of that shape might allow me to very accurately find the volume of it, okay? Questions on this? Volume, capital B times H for prisms and cylinders. Tomorrow, when we talk about pyramids and cones, it's a very, very, very easy adjustment to that formula. If we can compare a cone to a cylinder and a prism to a pyramid, very, very easy adjustment.